So this is some tree. Is this a binary search tree? Yes or no?
Yes.
Yes, it is.
Okay, remember the property, the symmetry property. Everything on the left side must be smaller than the node. Everything on the right side must be larger. So this is a binary search tree. Now what we do is we're going to put weights to determine the difference between the height. Okay? Like, why do we have to do that? Remember one thing, when we were studying the BST, we said that if the tree looks like this, okay? The tree looks like this. We call this thing a complete tree. What's good about the complete tree is that its runtime is going to be exactly log of n. Okay? If the tree is not a complete tree, if you have something like this, okay, this is kind of skewed. So this may give you a time which is close to O of n, which is not what we really wanted. This is not ideal. So the ideal thing is that if you can get a complete tree, every time you insert or remove something, you get a complete tree, okay? That's going to give you O of log of n. We can guarantee this by looking at this, putting weights on the tree. Now, look at this. We're going to see the difference. We're going to see the difference between the heights of the two sides. So look carefully what I'm going to do. I'm putting some weights. So starting from the lowest one here, 2. It has no children. There's no children on the left side, no children on the right side. So I'm going to use this symbol, flat line or hyphen. This means it's completely balanced. The difference between the heights on the left side and the right side is 0. Okay? Now, if you look at this one, 4. Okay? This node, 4. So on the left side, the height is 1. On the right side, the height is 0. So 1 minus 0 is plus 1. Yeah, there's a difference of 1. So what I'm going to do is I'm going to use this symbol. This means left side, it's 1 longer. Okay? It's 1 longer on the left side. Okay, let's come to 9. So, of course, left side is 0, right side is 0. The height is, yeah, starting from here. So 0 minus 0 is 0. It's going to give me this symbol. Okay, let's look at 8 now. So starting from 8, let's go deeper. So 1, 2. Okay, 1, 2. So on the left side, it's 2. On the right side, it's 1. So larger minus smaller, 2 minus 1, it's 1, which means I'm going to use this symbol. I'm going to say it's 1 tilted towards the left. Okay. Now let's look at another tree. I'm going to create another tree, and we'll see if you can put some weights on it, just for the sake of practice. Okay, let's see if we can put weights on this. So start from the lowest one, that will be the easiest. So here we use a flat line or difference 0. This would be difference 1 to the right side, okay, because left side is 0, right side is 1. So 1 to the right. This one, of course, is flat. Okay, here the depth of 2 from 4, or the height of 4, is 1 and 2 on the left side and 1 on the right side. So 2 minus 1. Remember, the left side is longer, so I'm going to use this symbol. Okay, same goes here. Of course, this is going to be flat. This one is going to be 1 left. Okay, 1 left. Now look at this one. So start from here, go for the longest branch. Okay, longest branch. So this is 1, 2, 3, 3 jumps. On the right side is 2 jumps. So 3 minus 2 is 1. So I'm going to use this symbol. So far, so good? Any questions about this?
Yes, Doctor. But why are we doing this, Doctor?
Okay, wait, I'm coming to it.
Oh.
All right. Now, why did we do this? Okay, if you look at this, you can see the single tree looks almost like a complete triangle, almost. Okay, there's a difference from the longest height on the left side and right side is 1. Okay, the difference is only 1. Look here, the difference is only 1. So imagine if I have a very long tree. Okay, let's say the depth is 1000. Okay, the difference of 1 will not matter because now the tree is going to look like this. This would be unreachable somehow, let's say. Okay, so from here to here is, if this is 1000 height, okay, from here to here, this is height minus 1, and of course this would be plus 1. So height minus 1 plus 1 will give you the total height. So what we're trying to say is, if you look at O of log of n, okay, we're saying the same, that the tree is going to give you O of log of n runtime. So if it is a complete tree or an almost complete tree like this one, okay, where the maximum difference between the heights of the longest branch on the left and the right side is 1, okay, this is okay, this is acceptable, and this is still going to give you log of n. How? Okay, imagine, remember the log? So we start from 1, 2, 4, 8, 16, 32, 64, 128, okay, and so on. 128, and so on. Okay, if you look at 1024, just to make sense, so n equals 1024, log of n is going to be 10. Okay, I'll pick 10 because it's an easier number to remember. So 1024, 10. Now what we're saying is, let's say we don't get 1024, we get 1020. Okay, we get maybe 1010, maybe 1008, some number like this. All of these numbers are pretty close to 1024. Bottom line is, doing a log for this is going to be close to 10. As long as I can guarantee that my tree is going to look like this, okay, it has this shape, even if there is a difference of 1 height, that's okay, because the runtime would be still close to log of n. Okay? Did I make myself clear, or do you have any questions?
No, clear, Doctor.
Can we have example, Doctor?
Yeah, I'm coming to it.
So, Doctor, if it's the difference is not big, I will not. I will. The difference of the log especially will be much even less than the difference in the length of the tree.
See, that's the idea. What we want to do is we want to have an almost complete tree. The complete tree is not always guaranteed, okay? Because maybe you have some less data. We're going with the log, so you're supposed to have exact this number. So here we're supposed to have 1024. Let's say you don't have 1024, you have 1008 or 1010 or 1020, something close to it. So we can still consider this equal to log of n, because if you start from here, okay, so you go downwards, because this is also a BST, so you go right, left, right, left, right, left. The maximum you're going to go down would be 10.
Yes.
Okay, which is giving you log of n time.
That's clear now.
Okay, so again, reflecting on this, why are we putting the weights? We're putting the weights because we want to make sure that the tree is going to be an almost complete tree. Okay, let me show you some examples where we don't have a complete tree. Okay, so again, go with a similar kind of tree. Okay. Is this an AVL tree? We say that, a tree having a maximum difference of 1 is fine. Difference between the left side and the right side. So let's quickly put weights on it, and you can tell if this is balanced, if this is AVL or not. So this is flat hyphen, okay, difference 0, difference 1 left, difference 0, difference 1 left. So as long as the difference is 1, that's okay. Ideally, we want to have 0, but again, that's not always possible. So 1 is fine. Okay, this is almost like a complete tree. I already showed you this photo before. Okay. So still from here to here, this is the height of the tree. Okay. And we say this thing n equals to the power height minus 1. If you want to search something in there, the maximum is the height of the tree. Okay, maximum number of searches is going to be the height of the tree. So which is in this case would be 3, because height is 3 here. Okay, let's look at a tree which is not an AVL tree. I'm going to show you a tree that looks just like this, but now this is not an AVL tree. And we'll see why. So if I simply put 1 over here, okay, notice this is also BST. But now let's look at the heights. So of course this is flat, 1 left. Okay, this is flat. Like here, on the left side the height is 2, the right side height is 0. Okay, so this is 2 and this is 0. So difference would be 2. So I'm going to use 2 lines. Okay, 2 lines identifying that the height difference is 2. Okay, this is a problem. Okay, look at this one. So height on the left side is 1, 2, 3. On the right side is 1. So this is 3 and 1. 3 minus 1 is 2. So we're going to go with this shape, 2 left lines. Okay, so this is a problem, and this is not AVL. Okay, this tree is not AVL. Why? If you look at this tree, okay, it looks like this. We have a height difference of 2. This is the height, which is 4. Okay, so minimum is 1 and maximum is, okay, on this side. So there's a difference. The maximum, sorry, I should go like this. Maximum minus minimum. Okay, it's 2 plus 2. So that is a problem, and we're not going to accept this as an AVL tree. Remember, it is a binary search tree, but it's not an AVL tree. Does it make sense?
Doctor, how much the height for the road should be?
No, we don't care about the height of the root. We're only looking at the difference between the heights on the left and the right side.
Yes, I mean the difference, yes.
Yeah, so 0 is acceptable, 1 is acceptable. Okay, more than 1 is a problem. Like here, this is 2, that's wrong. Okay, let's show you another tree. Look at this one. Okay, if I want to quickly go and put heights. So flat, flat. This is also flat because on the left side is 1, right side is 1. This is flat. This is what? We can say 1 left.
1, yes.
1
2
left.
minus 1.
1 left.
We can say 1 left. Here, this is flat. This one is going to be?
Now, doctor, isn't it 2 left?
No.
Because
this is determining the difference of the height, okay? So here's 2, here's 1. 2 minus 1 is 1.
Okay, clear now.
Now, how about here? This is 1, and this is 1, 2, 3.
So it's 2 to the right.
So 2 to the right. Okay, how about this one? So here is 0. Here, look at the longest branch. 1, 2, 3, 4. 0 and 4.
4
okay?
to the right.
So we can put 4 lines. Okay, but remember, we're saying that 0 and 1 is okay. More than 1 is a problem. So we don't really have to put 4 lines. We can simply put 2 lines. That's enough. Okay, 2 lines means that there is a problem and we have to fix this problem. Is this clear? Does it make sense?
Yes.
No, Doctor. For the third circle from the root and the right.
This
Starting
one?
from the root. Yes. Why we put 1 from in the right?
So look, this is telling you the difference between the heights on the left and right side. Okay, so left side is 1, 2, right side is 1. So 2 minus 1 is 1. This is why it's 1 tilted towards left.
Okay, but it will make a difference if we put the 1 in the left.
Come again, what?
The 1 we put it in the right. That equal from 2 minus 1. Yes. It
No.
will make a difference if we put. Oh, okay.
This is left side, okay? This is tilted towards left. Left side is longer than the right side. This one is right side. Okay, right side is longer than the left one. Same goes here. Everything is on the right side. Right side is longer than the left side. Okay now, or still?
Yes, yes, it's clear.
Okay, so now what we have to do? So we have to put heights. Okay, this is very important. So in an AVL tree, we have to write a method called set heights. Okay, the job of this method is to take the tree and store heights in the tree. Okay, so we will know the difference between the heights. So you'll be able to put the markers. These markers tell the difference between the heights on the right and the left side. Right. AVL suggested, okay, the 2 people that I mentioned before, these people, they suggested that every time you insert and remove, okay, we're doing an extra effort now to put heights inside the tree. But this cost, okay, of putting heights in the tree is not that much, because if I try to insert or remove something, remember this is a binary search tree. So if I try to insert or remove something, I'm going to decide to go right, left, right, left, right, left, right, left. So you're going only in one direction. Okay? So here's an example. Let's say this is some tree. Again, we're just using the same kind of tree. Okay, so if I try to insert 40, let's say I want to insert 40. Okay, before we insert 40, let's quickly put the weights in there. So this is 1 left, flat, flat, 1 right, 1 right, and 1 right. So there's no problems. There's no 2 lines, which means this is already an AVL tree. But now if I try to insert or remove something from this tree, okay, this can create problems for me. Let's try to insert 40. So we start from here, okay, 40 is bigger than 8, so we go right. So of course, I'm going to visit this one. We go right, okay, we're going to visit this one. We go right, we're going to visit this one. Go right, visit this one, and then insert 40 over here. Right. When you insert 40 or insert any node anywhere inside the tree, what's going to happen is, okay, the heights for this branch is going to change. Okay, how so? Look carefully. Now this one is going to become flat. This one will become, it was flat before, but not anymore. Now this is 1 right. This one becomes 2 right. This one becomes 2 right. This one also becomes 2 right. Okay? So what we're saying is, whenever we try to insert or remove something from our tree, in this case we're inserting something, it may change. We have to go and change the heights in every single node. But the cool thing about the AVL approach, okay, is that the maximum number of changes that you have to make is log of n. Why? because we're changing only one branch. Okay, we don't have to go and worry about the rest of the tree. The rest of the tree will not change. Okay, the only thing that will change is the branch. So this means that adding or updating the heights in the same branch is not an extra cost. Okay, so if the total runtime of the tree is O of log of n, adding this thing will still be log of n plus log of n is still big O of log of n. So this is acceptable. Did this make sense to you? Okay, so what
Yes,
we're saying is adding / insert or remove a node in AVL tree. Okay, its cost is O of log of n plus the cost of setting heights. It's also O of log of n, which means the overall runtime would still be big O of log of n. So as long as we're doing this thing, that's fine. We're going in the right direction. The runtime is still going to be big O of log of n. Okay, so this is some binary search tree. Let's see if you can put weights on it. Okay, what should be this weight? Yes, anybody? Nobody? How many people are there? Yeah, 12 people in
what was the question, Doctor?
What marker should I put here? We have this, or this. Which one should go here?
Here flat. First one.
Okay, this is flat. Here,
Flat also.
flat. This one?
From the right one. From the left.
One left. This one?
Flat. No, from the right.
One right. One right. Okay, this one?
Flat.
Flat. This one?
One right.
One right. This one?
Two right.
Two rights. Okay, this one?
Flat.
Flat. This one?
One.
Right.
You sure?
Two from the left.
Two left. Okay, why? Look here, 1, 2, 3. Here it's 1. So 3 minus 1 is 2. 2 left. Okay, how about here? What should we do?
2 minus 1, I think.
Look at the longest branch. Here the height would be 1, 2, 3. And here 1, 2, 3, 4. So 4 minus 3 is 1. So it should be 1 right.
Yes.
Okay. Do you see any node which has a problem? This is a problem. This is a problem. Okay, both of these are problems. Why are they problem?
Because bigger than 1.
Yeah, the height difference is more than 1. Okay, so that is a problem. So how do we fix the problem? Now, do you understand now?
Yes,
The weights.
Clear.
Okay, so putting the weights identifies which nodes have a problem. Once we know that which nodes has a problem, what we can do is we can go to step number 2. Okay, let me scroll back to the first page. So we're done with this one. Now we're going to look at rotations. Okay, so once you have identified where the problem is, we can start rotating. Okay, so rotations. Okay, so this is the contribution of the AVL. Okay, that's what makes it magically faster than binary search trees. This is what guarantees that the runtime would be big O of log of n. So we have four kinds of rotations. We have left rotation, we have right rotation, we have left right, and we have right left. It's kind of similar to what we studied yesterday with the binary search trees. But here now the idea is that we're going to rotate and change the shape of the tree, so the tree will be balanced, or AVL balanced. All right. Now I have written this thing here. Sorry, not here. In my code, if you scroll up, okay, this is some theory. This is necessary. So these are kind of rotations. Now let's try to look at each one of them. So I'm going to explain it in a different way, okay, because this was written, I don't know, 4 years ago. But if you want to go back and look at it, it's there, okay? But here I'm just going to try to explain it using these things. So I'll just show you the shape, and then one by one, we're going to look at solution for each one of them. So let's first do the single rotations, okay? These are called single rotations. Single rotations. These two are called double rotations. All right. So what does the shape of the tree look like when we're trying to solve the problem? So here's my tree. Okay, this is my tree. And if I put weights on it, I see that there's a problem on this node, because there's a difference of 2. It is possible that we have some other stuff over here. Really don't care. Okay, there must be something here, something here. So we can say that this is some subtree. Okay, clean this up. So this is some subtree. Okay, you don't even have to put one node. You can simply say that there is some subtree over here. Let's say this is subtree A, subtree B, subtree C, subtree D. They can be only 4, not more than 4. Okay? Because there's only 4 possible ways of connecting to these 3 nodes. All right. So this is my left, because it's left. Okay, left. This is the shape of the tree. And it's creating a problem, and the problem is here. This is the node with the problem. All right, let me show you this one. So obviously, as this is left, we're going to have right. So you're going to have something like this. Okay. If you want to put weights on it, so we're going to get this one to be flat, single right, and double right. Okay, or 2 rights. And then we have some subtrees. So we can have something over here. We can have something over here. We can have something here and something here. Again, I can call this one A, B, C, and D. Okay, so far so good? Just for the sake of understanding, yeah. I'm going to put some values over here. Okay, I'm going to say that this is Z. Okay, Y and X. X is smaller than Y, so it's on the left side. Y is smaller than Z, so it's on the left side of Z. D must be larger or smaller than Z?
D smaller than Z.
You sure?
Larger.
Should be larger. D should be larger than Z. It's on the right side. Okay.
Yes. Yes.
So this would be X. This would be Y. This would be Z. Okay. So X, Y, Z. Y is larger than X, so it's on the right side. Z is larger than Y, so it's also on the right side. Okay. So these are my single rotations. Now let me show you what this shape looks like. Left and right. So you're going to have a tree that kind of looks like this. So we go left first, and then we go right. Okay, so here I can say this, that this is Z. Okay, this could be X, this could be Y. Yes? So Y is smaller than Z, so it's on the left of Z, but it's larger than X, so it's on the right side of X. And again, you can have a maximum of 4 subtrees here. So you can have A here, you can have B, we can have C, and we can have a D. Okay, so again, if you want to put the weights here, you'll see that this is flat, let's say flat, 1 right, and 2 left. Okay, so this is left, right. All right, the last possibility, which is right, left, is a tree kind of looks like this. So go right, and we go 1 left. Okay, so everything is larger, and then this could be X, this could be Z, and this could be a Y. Okay, so I'm just putting these over here just to make you understand, although they don't have to be X, Y, Z. So this, we're going to have these 1 left and 2 right. Okay, so problem on the right side. Now, if you want to put the subtrees, okay, so we can have something over here. This is subtree A. We can have something here, subtree B. We can have subtree C. And you can have subtree D. Okay, so far so good. So if you look at it, this is giving you this kind of shape. This is giving you this kind of shape. This gives you this kind of shape. Okay, and this would be straight like this. There you go. All right, if you try to rotate these, okay, we can fix the problem. Now, I'm going to show you one by one how each one of them works. Okay, so far so good. Is this clear? So what we have seen so far is that these are the 4 possibilities. Okay, that your tree on the top node is not AVL. It's giving you a difference, height difference of 2. So let's go one by one. I'm going to take this one and then work with this. So let's copy paste this to the next screen. Okay, so how this is going to work. What we're going to do is we're going to redraw the tree, okay, so that the tree looks like this. Okay, so this would be X, this would be Y, and this would be Z. Okay, so X, Y, Z. Yani the one in the middle, this becomes the root now. So we're rotating. If you notice carefully, this kind of happens like this. Okay, this part is going down. Okay, so this is showing you the tree is rotating this way. So Y becomes the new root, X stays on the left side, and Z goes on the right side. Now, notice something. Which subtrees we have to change? Okay, X has children A and B. Do we have to change any of this or no need?
No, will be the same.
Yeah, it doesn't change, okay?
Yeah.
It stays as A, this one stays as B. It doesn't change. All right. One other thing, the Z dot right is subtree D. So we can still maintain this.
Yeah.
We can still have B. No need to change that.
Only just add the C to the left of Z.
The only thing which is going to change is the subtree C, okay? And this is going to change, the connection between Y and Z. Now, if you want to put markers on it, you're going to see that the tree, resulting tree becomes flat or balanced, AVL balanced. How to achieve this? What things that we have to change?
We just need to make Y as the root.
Yeah, so I have to say Y dot
Parent.
right equals to Z.
Yes.
Okay, Z dot left is equal to C, subtree C. Okay, that's all. These are the only 2 changes which have happened. Everything else stays the same. So far, so good? Okay,
Yes.
how about the Parents. Do we have to change the parent of C? Should I say C dot parent is equal to Z now?
Yes.
Yes?
Yes.
And I have to say Z dot parent now equals to Y. Z dot parent equals to Y.
Also, y dot parent equal null.
Yeah, and also Y dot parent. So whatever is the Y dot parent should become equal to Z dot parent. Okay, but I think this line should come over here. So let's try this thing on the top. Okay, so I'm going to put this in a different color. So before any of this, we have to say Y dot parent equals Z dot parent. Okay, is this clear? Does it make sense to you?
Yes. Yes, clear.
Let's look at an example. Okay, so this is our concept. Let's look at an example. So I have some tree and I want you to rotate it left, left. Okay, so here's 10, 8, 4, 5, 20. Okay, let's see which case applies. So to see this thing, you have to put the weights on it. So this one is flat, this one is
One right,
One right.
one right, this one is
one left.
two left.
Two left.
Yes, two left. Yes.
Two left, this one is flat, this one is two
Two
left.
left.
Okay, so we have a problem here, we have a problem here. Like a rule of thumb, start from the node which is at the lowest possible problem level, which is this one. So I'm going to start from here. Okay, sorry, my mistake. Let me fix this. This is not a very good example. Okay, I'll change that. Let's go with this tree. Okay, so starting from here, you can draw and you can see this shape. Okay, starting from the node with the problem, go down towards the longest branch. So it gives you this shape, which means this is this rotation problem, left, left. So now what we're going to do is we don't have to touch the rest of the tree. You only have to fix this part. Okay, so notice here, we don't have any subtrees. This should have been A, B, this should have been C, and this should have been D. But here we don't have it. So what we can do is we can redraw the tree, okay, this part. So which one becomes a new subroot for this one?
4.
4. Okay, left would be 2, and the right will become, so this is 8, this is 4, this is 2. So what happens is this becomes 4, this is 2, and this becomes 8. Okay, and the rest of the tree stays the same. So we have 10 and we have 20. Now if you go and put weights on it, see, is this AVL balanced? Flat, 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 and one left. So remember, one is okay. More than one is a problem. So this is AVL. This means that we had a tree which had a problem. What we did was we applied a left-left rotation on it to get this tree, and now this is an AVL tree.
But Doctor, the 4 is not flat.
4 is flat. Why? Remember, this is telling you the difference between the heights.
Okay.
So 1 minus 1 is 0. This is 2 minus 1 is 1, so 1 towards left. Is this okay? Is this clear?
Yes, it's clear, Doctor.
Yes, doctor. Yeah.
Okay, so we're done with this one. Now I'm going to show you the other single rotation, which is right, which is very similar to what we have. So copy paste this. Okay, so here's the right rotation. Now, if you look at this particular tree, we have identified a problem, and we're saying starting from here, we go down to the longest branch. Okay, so it's going to give us this shape. Now, if I want to redraw it, okay, what I did before, I'll just do the same thing here. So now what's going to happen is we can promote this node as the root. So we can have a y, okay, z, and we have x goes on the side. Okay, remember, okay, instead of confusing you, yeah, let's keep them as labels and not values. Okay, so these are just labels. So y, x, and z. If you go and reattach the subtrees, so we're going to have A, we're going to have B here. Okay, so notice what changed. A will not change. A is still connected to X. Okay, C and D are not going to change. They're still connected to Z. So we're going to have C, and we're going to have subtree D. What's going to change was B. Previously it was connected to Y, but now this will be, I'll use the red color, just to be consistent. So this is going to be B. So what changed? Which one changed here? This one or this one?
The Y, doctor, change.
The left one.
Yeah, left one, this one. Okay, so these changed. All right, so to fix this, what do we have to do? Of course, we have to go and change the parent of Y now. So we're going to say Y dot parent is equal to Z dot, no, X dot parent, because previously X was the root. Okay, now what else changed? So now we have to say Y dot left equals to X.
X.
X dot right equals to B. Okay? X dot right is equal to B. What about the parents now? So we have to say X dot parent now is Y, and B dot parent equals to X. There you go. So it's going to take care of it. Right, let's look at an example for this particular case. I think I drew a tree like this before. Okay, so I have a tree like this. Let's see, is this AVL or not? So quickly put the weights on it. This should be flat. Come on, I need somebody to speak up. What is this one?
This one, one
left.
One left. This one?
Two right.
Two right.
To the right. This one?
Flat.
Flat.
This one?
Two.
Two.
Two left.
Two left. Okay? Two left. Right, we have two problems. We have a problem here, we have a problem here. So I told you, rule of thumb, look at the one at the lower level. This usually fixes the problem. So start from here. Okay, what shape do you get? Are you getting this shape?
No.
Nope. Okay, so I'll fix this straight. Okay, let's put a 7 here. Sorry, this should be flat, and this should be one right. Now, if you look at it, you get this shape. Okay, so let's fix this. So which one should become the new subroot?
6.
6. Left would be 4.
4.
Right would be 7. Okay, and the rest of the tree stays the same. We don't have to change anything. Only this part changes. Now, if you go and put the weights on it, okay, so this is flat, flat. This is also flat, flat, and one left. So this is AVL. So now we see that this is left-left rotation. After one rotation, we converted our problematic tree into an AVL tree. Same goes here. Okay, we had this problem, we rotated it, okay, and then we have an AVL tree. Right. Are you guys following? Is this okay? Should we move ahead? We have time.
Yes.
Should we move ahead? Look at the other two rotations.
Yes, I think it's clear that
It's okay.
Yes.
Only one person responding today. I don't know why. All right. So let's look at the other two rotations. So these were the single rotations. Now we're going to talk about the double rotations, the one that looks like this and the one that looks like this. So I'll copy one by one. Okay, so this is left, right, and let's see how to fix this. Now, in this particular rotation, what we're going to do is we're going to promote this one as a new root. Okay? Remember, in the single rotations, we were picking the one in the middle. We picked this one. Here we picked this one. Okay? But for double rotations, if the shape looks like this, then we pick the lower one. Okay, how does that work out? So y becomes the new root. Okay, of course, we're going to have x and z over here. Okay, so here, which one changed? Both of them or one of them?
Both of them, Doctor.
Both of them changed. Okay, now we're going to go and reattach the subtrees as before. So this is A, B, C, and D. Right here, which one changed? So x on left is still A.
Yes.
Okay.
So the B changed. It
B,
was under Y and now it's under X.
C also changed.
Yes.
Okay, and Z dot right is still D. There's no change there. Okay, so how is this going to work out? Right. So again, what we did before, if I'm writing code for this, so I'm going to say now y dot parent should be equal to the parent of Z before everything. Okay, now what else changed? So let's go one by one. So now we're going to say y dot left equals to x, y dot right equals to z. Okay, how about this one? X dot right equals to b, and z dot left equals to c. Okay, so far so good. Hey, what about the parents? Let's fix the parent.
Yeah, x dot parent equal y.
X dot parent equals to y.
Z
Z dot parent equals to y. Okay, B dot parent equals to
x.
X, and C dot parent equals to Z. Yes, C dot parent
Yes, Z
equals to Z. So there you go. Now this one looks a bit more complicated than this one. Okay, here we had only 5 lines of code, but here we have almost nine lines of code. Okay, let's look at an example for this and how this works. So this is called double rotation. Double rotation. Why? Because 2 rotations happen. Okay, let's look at an example. So here's some tree. Okay, let's try to put weights on it. So this one is going to be flat. This one,
flat.
flat. This one,
One to the left.
one left. This one,
One to the right.
one right. Flat. And this one.
Two to the left.
The longest is 1, 2, 3,
Three.
and 1.
Yeah.
So it should be 2.
Yeah, two to the left.
Okay, so this is the node with the problem. Okay, let's drop down from here to the longest branch. So I'm getting this shape. Okay, which is this one, this kind of rotation, left-right rotation. So quickly go and identify the ones that need to be changed. So this becomes my Z. This will be X. This will be Y. Okay, this is my subtree A. This is subtree B. There's nothing here, so my subtree C is empty. And this is my subtree D. Okay, so redraw the tree. So which one becomes the new root now? 9, 7,
9.
10.
9, doctor.
9 becomes the new root. Okay,
So it's-
7 is here, and 10 goes to the right side.
Yes.
Now they're going to reattach my tree. So A, B, C, and D. So this would be 5. This should be 8. Yeah, there was no C, but there is D. There you go.
Don't.
Okay. Does that look like
Yes.
a balance tree now?
Yes.
Let's check. So flat, 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 one right, flat. So we don't have any problems.
Yes. Doctor, this procedure seems to be systematic. Like there is no need to just you need to know the type of the tree of the
Rotation.
rotation. Yeah, is it
Exactly.
left?
So you have to determine which rotation is it. Okay.
Yeah.
And how would you know that which rotation is it? Easy. Okay. So the node which has a problem, look at this one, and then go check the two nodes deeper. Okay, which one is it? So it's going to give you left, left, okay, longest height. Left, right, right, left, right, right. How can we know the heights? Of course, the nodes are storing the heights. Okay, so you can quickly check which side has a problem. It's very easy to implement in the code. It's just a few if conditions and that's it.
And then everything is clear steps, and there is no need to consider anything or think about it. You just need to know the types, and then it's a done deal.
Yes, exactly. Okay. Let's look at this one, the last one. Okay, this is the right-left rotation. Let's see how this is going to work out. Okay. So again, like what I said before, here what we do is we promote the one at the lowest level. Okay, this is the one which has a problem. So we try to rotate it this way. Okay, so I'm going to redraw this. So we're going to have Y on the top. Okay, then we have X, and then we have Z. All right, and we simply go and reattach our subtrees. So here you're going to have A, B, C, and D. Very good. Like here, which ones had problem? Or which one needs fixing? This will change.
Yes.
This will change. This will change. And this will change. Okay. So let's see how to write code for this. So again, for the parent, of course, the same line will repeat. So we're going to say y.parent equals 2. Previously, x was the root, so x.parent. Okay. Now let's look at the code for these. So we're going to say,
Doctor,
yeah.
runtime wise, is it better to write y.parent equal x.parent, or just write y.parent equal null? Because it will not have to go check what is the parent of x.
No, we cannot say null because maybe there's something up over here. I showed you something.
Oh, okay, okay. I now see.
It may have a parent. Most
Okay.
likely it is going to have a parent. Okay, so we have to say that. All right, so y dot left equals to x, and then what else? Y dot right
Y dot right
equals z.
equals Z. Z dot left equals C.
So let's go systematically.
X
So x dot left equals v, and z dot.
Z left.
Sorry, it
This
should be
one
right.
is yeah.
Yeah, let me fix that. So x dot right equals b, and z dot left equals c. Okay, and now the parents. So b dot parent equals x, x dot parent
Equal Y
equals y, and c
C
dot parent
equals Z.
z, and z dot parent equals y. Okay, so there you go. Let's look at an example for this particular case. So again, okay, so I've created just a little bit of a tricky tree. Let's see how this works. Let's go and put weights in there. So this is flat, flat,
Flat.
flat. This one,
1 to the left.
one left, flat. This one,
2 to the right.
two to the right. Okay. So again, this is the problematic node. We start walking down to the longer side. So we go this way, and then we go this way. Okay. So we're getting this shape. Okay. So let's identify our subtrees. So obviously this is going to be A, this is B, this is C, and this is D. Now all I have to do is redraw the tree. So the new root will be
12.
12, left would be 8, right would be 20. Okay, and then it's simply going to attach the nodes. So this is 2, this one is 10, this one is 17, and this one is
30.
Okay, remember one thing. The beauty about this algorithm is that even after you rotate, your tree is still a BST. Okay, remember AVL is a subset of a binary search tree.
Yes.
Okay, I would like you to insert 9. Okay, where does 9 go?
To the right of the 7.
To the
Right,
right.
right.
So we go and insert 9 over here. Now, is this an AVL?
No.
So this is an additional step on top of BST. So quickly go and put the weights. So this is flat, 1 right, 2 right, 2 rights. This is flat. So we have this problem. Okay, walking down from 5 gives you this shape. So what kind of rotation is it?
Right, right.
This
RR.
right rotation. Okay, so what we have to do is we have to redraw the tree. Okay, of course the root will not change in this case, but here the root becomes 7. So we're going to have 5 and we have 9. So quickly check after you've done the rotation if your rotation was correct or not. The resulting tree should be an AVL. So this is flat, 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 and 1 right. So that's okay. This is AVL. Okay. Next, somebody says, I want to insert two. So this is my tree now. Where does 2 go?
We set for the new tree.
Yeah, so in this tree, where does tree 2 go? Where should we insert 2?
To the right of 1. Right of 1.
Right of 1. Very good. Okay. Check. Is this AVL? So flat,
Yeah.
flat, flat, one right, flat, and flat.
Flat.
Okay,
Yes.
so this is an AVL. Okay, so even after inserting, we did not have to rotate. So we learned something now, that maybe, it depends on the shape of the tree. Maybe when you try to insert or remove something, even after insertion or removal, your tree does not need rotation. Okay, so this means that if I want to insert 10 keys in my tree, it does not mean that I have to rotate it 10 times. Maybe it could be less than 10 times. And remember the cost for rotation. We didn't talk about this. What's the cost of rotation?
Should it be log n?
No. How many nodes you're changing? It's constant.
For
Constant number of changes. Okay, how so? Now you have to ask me why. Why constant? Look, regardless of the size of the tree, maybe the tree is very large. Okay, the maximum number of changes for each rotation is only these lines of code, which is what, 8 to 9 lines of code, that's it. So this is constant. Okay, so here, let's see. Let's try to insert something else in there. So I want you to insert 12. Where does 12 go? So quickly redrawing the tree. 3, 1,
12
2,
will be to the right of 9.
5, 9, and there's 12. Okay, is this tree AVL?
No.
Does it look like AVL? Let's check. So flat, one right, flat, flat, one right, and this one? 1 or 2?
2.
1.
2 or 1?
1.
1, 2.
We have 3 on the right and 2 on the left.
Yeah, so the difference is 1. So is this AVL?
Yes.
Yes, it's still AVL. Okay, now if somebody says, hey, I want you to remove 2. Which case applies for removal? This is 2.
Case number 0.
Case number 0, so simply go and remove it. Okay, so after removal, my tree now looks like this. So 3, I have 1 over here. This is 7, 5, 9, and 12. Is this AVL?
No. We have 2 at the root, 2 to the right.
Let's put the weights quickly. And on the root, we have 2 rights. Okay, so do the rotation now. Which rotation is needed?
RR.
So RR. Start from here, go to the longest branch, it's this one. Okay, so let's go and identify your subtree. So here's one subtree A, B, there's no C, and this is D. Okay, and all I have to do is just reassign. So which one becomes a new root?
9.
In the single rotation, the one in the middle.
5.
Okay, so 5 will be the new root. We have 3, and we have 9. And here we're going to have 1, B is 5. Oops. Did we have 2 5s? Oh, sorry, this is 7. This is 7. Okay, so there's no C, and this is 12. Okay, so quickly check, is this AVL? So flat, 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 one right, and this is also flat. Very good. Here's an AVL tree. Again, if you want to check, you can check again. This must be a BST. So every single node, okay, should have the symmetry property that we studied before for BSTs. Okay, so that's it. This gave you some practice. So we finished with AVL trees now.